Hi, it's Bruce again in my Colorado Rocky Mountain lab. And I have here one of my three Philips counters. This one is a PM6612. It's an 80 megahertz counter. Um, and it has functions to measure period, time interval between the two port, and it also calculate the ratio between two incoming frequencies through those two ports. And it has three different ranges of frequency time base, zero point 0.1 second, 1 second, and a 10-second interval to give you a maximum resolution for your low frequencies. It has two sensitivity controls. It'll work 0 to 10 millivolts, or pull out the control at 0 to 200 millivolts. We can go 80 megahertz on A, and less than 100 kilohertz with the left-hand button. So she'll go up over 80. We'll check it out and prove that. And then the B channel can measure up to 10 megahertz, and that's what we use to do the ratios and so on. And we'll explain what we mean by that when we do the demo. In the meantime, let's take a quick look around this unit. I mean, you've seen the front panel now. It's attractive. Got minor scratch or two, but most people wouldn't even notice. Very nice looking cabinet. Good shape. Nice stand. It's working well. Good feet. And let's see if we can turn that around. Here we go. And give you a look at the rear end. And you notice on the rear end to the left-hand bottom side, we've got external standard or internal standard. You switch up or down for that. So you can use this on your bench using your bench standard if you wish. We have external battery inputs here. It will accept a special battery if one wanted to purchase it. But you've got a switch that goes from mains to internal battery. And we have an input for B and C and a standard output. Actually, the standard output on this unit connects to the internal time base, and it outputs the signal from the OCXO that I've installed inside. So honestly, you have a means to tap into that OCXO, and you could use it to run your bench. The only thing you'd need would be a distribution box with multiple outputs, and you could run whatever runs off of 10 megahertz. And you'd have OCXO quality for everything. Okay, well, we've hooked up a Fluke distribution amplifier. This is a model 203A made by Fluke. It's that unit right here ahead of us. And as you can see, the power's on. We're registering something on the meter over there. You're wondering what. And we see that we've got this knob here with 12 positions as a level check. And then there's a power supply, and then there's 3 preamps. What this does is it'll take 3 different frequencies of input. It'll take 100 kilohertz from a 100 kilohertz oscillator, a 1 megahertz oscillator. It'll take that signal, and it'll take a 10 megahertz oscillator. So you can have 3 different OCXOs on your bench and provide those 3 signals into the back of this unit, and it provides you 3 different controls to control the gain that this unit will provide to those signals coming in. And then each one of those 3 signals has 4 outputs available. So channels 1 through 4 are for the 100 kilohertz Channel 5 through 8 are for the 1 megahertz, and channel 9 through 12 are for the 10 megahertz. And there is a power supply check here. We're getting 5 volts out of the power supply, which is what we want. And then here's channel 12. We've got 1 volt of output under load because I'm feeding that signal out to something. Here's channel 11. That's a 10 megahertz signal with a little over 1 volt. Channel 10 is a 10 megahertz signal, a little over a volt, and the same with 9. So all 3 of those have an output of 10 megahertz, and they've been adjusted. Channels 1 through 8, there's no signal coming in right now, so there's nothing there registering. Then on top of the unit, you'll see that we've got 10 megahertz, 1 megahertz, and 0.1 megahertz. There's 4 adjustment slots on the top for each one of those frequencies, and that allows you to adjust each channel so that you get the voltage that you want being provided on the output. So I've adjusted it for roughly a volt on each output. And what we've done is we've connected the Philips that has the 10 megahertz OCXO in it that I'm very happy with. And we've taken the output from the rear of the unit and we fed it into the input, the 10 megahertz input on this Fluke distribution amplifier, and that gives us 4 outputs. One of which right now, channel 12, is running up to another counter. And that other counter right now is reading 10 megahertz to 3 zeros. And we can increase the time on that to see if we can pick up an additional count. We'll let that go for a minute while it's doing that. And at the same time, I'm feeding this is a 1 megahertz, no, I'm sorry, feeding a 10 megahertz signal out of this PTS right back into the channel A on this Philips, just to prove that the Philips is still capable of reading the frequency, which, let's make it a different frequency so there's 12 megahertz. So it's reading 12 megahertz at the same time that it's putting out a signal to the distribution amplifier to be used right now by another piece of equipment up here. So yes, you can run your bench with a distribution amplifier and using this OCXO that's in this counter, which is good. I mean, it's a very good OCXO. It's registering very closely to my my rubidium standard right now, and I haven't touched this thing in months, so I'm quite amazed by that. And there's a lot of benefits to running your bench off of a common OCXO. Any generator that has a 10 megahertz input on the back of it, meaning that it's got a counting circuit system inside that's generating 10 megahertz internally, and you can switch it to external. Then you run that generator off of the same OCXO. What comes out of that generator is going to be the same thing that you read on your counter, like within whatever the characteristics of the device are. Like in this case, the generator would put out within a hertz, and the counter would read within a hertz. And it makes everything come together beautifully. So recommend that to you highly, and I'm just demonstrating that this unit can be used as your master bench oscillator if you wanted to. All right. Input C on this back panel allows you to input from a bench oscillator externally into the unit, in which case you pop this switch down into external. And then the B output actually is the output of channel B. So if you have a signal going in, you can retrieve it on the back and do something with it on the outside as well. Okay, so we flipped the unit upside down and we've removed the bottom access panel. And here you can see the OCXO that I've installed into the unit. It went right into the same spot that the original time base went, which was part of the design criteria from Dan. Good job, Dan. And it's based upon a CTS 10 megahertz OCXO. Once the unit was built and installed, I zero beat against my rubidium standard and set the frequency on the OCXO. So once she's warmed up, she's locked in. Now we're going to put it back together and we'll take a few tests. Okay, well, we're back together and once again measuring the 10 megahertz from my bench standard. And at the moment we don't even see a hertz. There's 1 beat difference. And it could be the counter just doing a standard 1 count fault, or we could be a fraction of a hertz off and it's rounded. But in a moment it probably will go away. But it just went away. In any case, we've just proven here that we're measuring the 10 megahertz from my bench. And let's take it to 0.1 second time base. This would give us 10,000 kilohertz, 10 megahertz. Okay. Here's 10,000 to 3 decimal places. And then if we go to the 10 second time base, which, you know, you got to wait a little bit, but it will give us an additional resolution. There's 10,004 zeros. Let's let it go through one more count and just verify what we've got. Yep, it just finished. 10,004 zeros. So better than a tenth. So I'm guessing there's a count. Pretty standard for a counter to pick up 1 additional count at the end, but often it goes away. All right, so let's do some other testing. Okay, well, I've connected myself up to this PTS 500 up here, and we've dialed in 80 megahertz, and we see on the Philips that we're reading 80 megahertz. So indeed, this counter will read 80 megahertz. But let's just for kicks go up to 90. Oh, it'll read 90 megahertz. Probably not a good idea to do it for an extended period. It's not made for that, but it's nice to know that we have additional reserve. So we don't have a problem with that. Okay, I'm going to drop down to 1 megahertz here. Okay. So we just proved that channel A could read to its maximum. That was on the Sine. Now we have a positive square wave or positive pulse and a negative pulse that we can choose as an input. Let's give a check at those. Okay, well, we've hooked up the Philips counter to a Kronheit model 5100B. Also a very nice looking unit that soon will be up for sale. But in the meantime, we're going to use this unit to demonstrate the 3 different inputs that are available mode-wise under 80 megahertz. Right now we're feeding in about a 1 megahertz signal as shown on the panel. And we're feeding in a sine wave, and we've chosen sine wave, and we're reading the frequency. Now if I switch the Kronheit to a positive going pulse, we lost our count. However, if I pushed positive pulse, she's back again. But now what if I threw in a negative pulse instead? Well, the counter doesn't particularly like that. But if you push in the negative going pulse, it counts it. Back to sine. And we're not getting a good reading on that because we're feeding negative pulses. Now there's the sine wave. We have gone back up again. So our three different pulse types are available on the front panel to solve that problem. So we have the left-hand button, that's the less than 100 kilohertz. That's really a low-pass filter. So if you're going to be measuring in the less than 100 kilohertz range, you'd push that, and that would help eliminate RF above that frequency from interfering with you and maybe disrupting your readings. So low-pass filter. All right, right now we're feeding in a 1 megahertz signal, 999.99 something kilohertz, and if we push our low pass filter for less than 100 kilohertz input, notice that we lost the signal. The reason we lost the signal is that it's 10 times greater than 100 kilohertz, and it's been filtered out. Still there. Okay. Filter it out. And yet, if I was to change the frequency to something lower, like 100 kilohertz, there we see that the 100 kilohertz is working fine. If I go back to regular sine, 100 kilohertz is there. There is no high pass filter for it, so it gets through. But raise that frequency back up again, to a megahertz, and then try to go to 100 kilohertz, and we lose the signal. So it's filtering out successfully. That at least demonstrates that part. Let's go back. All right, we've got 999.995 kilohertz coming in from this little DDS generator here, so megahertz. Let's check the period. All right, there's for 1 decimal point. Here we're getting 1.000. So we've got 1 and 4 zeros with a 1 or 2 at the end for microseconds. 1 microsecond, 1 megahertz. So we're reading the period fine. When you're in the period setting, it says n equal 1, n equals 10 squared, or n equals 10 to the 4th. N is the number of period cycles that were averaged to get you the result. So when n equals 1, it's measuring every single cycle, 1 period. And as a result, they only give you 1 decimal place. If you average 100, then they've given us 3 decimal places with 100. And if you average 10,000, then they give you 5 decimal places. All right, so what am I doing now? Well, we want to check the ratio of A to B. So I have to have 2 signals. I've got to have an A signal, which right now I'm pulling A from my PTS synthesizer up there. I'm bringing in a 2 megahertz signal. We can verify that easily. There we are. We're reading 2 megahertz on A. And right now I'm on the ratio of A to B where I'm averaging 100 measurements, I guess a second, or 100 measurements at a time anyway. And we are getting a ratio of 2.01 at the moment. Let's call it 2. So it says that A is 2 times bigger than B, so if A is 2 megahertz, then B must be 1 megahertz. And that's what I attempted to set this crone height up at. And if we go to 10,000 counts or 10,000 averages for the display, then we see that we are 2.008, and it would be extremely difficult for me to adjust this dial on the crone height to get better than that. So the ratio is working fine. That's what I wanted to demonstrate there. Let's take a look at the count. And let's put our count at a speed that it's meant to work at. So we're going to take the A and B, we'll swap these inputs. And we'll turn this down to something that is more manageable. Okay, in order to initiate a count on A, I have to push in the StartStop button. It's a little nomenclature that's right here to the bottom, which reads memory on the top of that button. So I'm going to hit that, and we're going to start. We see that we're counting now. And we're counting at roughly a 10 hertz rate. This is what I have dialed in for A. And then if I want to stop the count, you see we've got up to 142. And then if I restart, then it starts over again. So the counter's working. Let's take a look at time interval between A and B. Okay, I think I've devised a little scheme here to demonstrate the time interval measurement. And what we're doing is we're using the DDS to provide us a square wave. Square wave goes in channel A on the Philips. The channel A right now is set to look for positive peaks. And then when the second half of the square wave goes negative, we've got the B channel looking for a negative peak. So it sees that negative going signal and it counts it, and it stops the count. So that's right at the edge of where it drops negative. So we're only counting for 1/2 of the full waveform going into channel A. That's only the positive half of the wave. If we're working at 1,000 hertz, then there is 1,000 microseconds in that 1,000, in each one of the cycles of the 1,000 hertz, because 1,000 times 1,000 is a mega. A microsecond is 1/1,000,000th. So there's 1,000 microseconds in one full one full kilohertz cycle. And then if you're only looking at half of that, then you're going to get, instead of 1,000, you get 500. So there's 500 microseconds in the positive part of the square wave. And then we shut it off and we measure again, and there's 500 mega. So you're going to get repetitively 500 microseconds showing up on the screen if we are measuring the 1 kilohertz incoming square wave properly. And we are. If I was to go to milliseconds, then we would see 1,000th of that. So that would be 0.5. So 0.6, we're off a little bit. If we drop our, you see it fluctuating there. If we drop our frequency now, and we're counting at 100 hertz, then we start to see 5.0 milliseconds for the 100 hertz. And if we drop that even more, well, let's see. Well, let's first go to microseconds. We see there's 5,000 microseconds now in 100 hertz, in half of the cycle time of 100 hertz. And if we go to 10 hertz, we now have 50 milliseconds for the positive half of the square wave, 100 milliseconds total in the wave for 10 cycles. And if we go to the microseconds, we see about 50,000 roughly. So we see that that's working. I'm not sure if this, I'd have to look at the specs again, but we'll try one cycle and see if we can handle this. And it's looking to me like it's not doing it very well. So I'm thinking one cycle is just out of its range for this particular function. I'll check on that and we'll get right. Well, I did check in the manual, and it's telling me that for the time interval measurement, we can use 10 hertz to 10 megahertz. So one hertz is out of its range, and that's why we're getting fewer counts here. So let's go back up to 10, and there we are again, back at 50. So that looks good. 50 milliseconds at a 10 hertz rate. That's for half of the square wave. So it looks like we're working fine. That really concludes everything here. And I'm going to wish you happy bidding. I will provide a manual and a specification sheet with the Philips. It'll be an operation and service manual, so there's schematics involved. And it'll be on a CD. And we'll see you again.